Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 6.4, which has to deal with work. Pretty simple title, and also will be a relatively short section. There's not too much to talk about here, and if you've ever done work in physics, this should be a nice refresher, hopefully. Generally, we have that work is defined by force times distance, and force is sometimes defined as mass times acceleration. All things that we're going to have to keep in mind. And generally, we usually have weight, or we have work rather, in either Newton meters or joules, or sometimes they're using pounds and distance, which they're typically called foot-pounds at that point. That's just some stuff about what force and work is. But because work is just force times distance, and we can think about distance as a difference like we have here of x sub I minus x sub I plus 1, that looks a lot like delta x. And whether force is constant or whether it's changing, we can define it as a function. And therefore, we get an integral that looks relatively similar because we can define it as the limits of the sum of f of x sub I times delta x, which is just the integral of the force times dx. That's how we can find work, which is pretty nice that it's that simple. To start off with the simple cases, we have what is called Hooke's law, which is going to be useful for finding the force necessary to stretch or compress a string. I should say spring, rather, not string. Spring. Okay. Where we have F equals kx. That's all we need for the force for Hooke's law, where k is what is called the spring constant, or it's basically just how stiff the spring is, which is just a constant value. Therefore, if that's all F is, then that means we take k of x, or kx, we plug that in to f of x, and we get the integral of kx dx. K is just a constant, x is just x, so we can do the integral of x, and we can even evaluate this as just 1/2 kx squared from a to b. That's all we would need to find the work to compress a string. I do want to keep in mind, however, that the best way to think about these is that if you have a spring, you want to consider the standard distance, or where it sits naturally, its natural length, as the origin. That's what I'll always recommend, to use the origin as the natural length of the spring. Then if it stretches or compresses, you can determine that by how far it's stretching or compressing from its natural distance. As an example, we have here, I'll keep a little bit of it up. Yeah, that's all we need. If the natural length of a spring is 0.2 meters, and if it takes a force of 12 newtons to keep it extended 0.04 meters, we want to find the work done in stretching the string from its natural length to 0.3 meters. Okay, well, if we think about this spring, something like that, we have that its natural length is 0.2 meters. So I'm going to keep the end of its natural length at the origin 0. So that means if you were to stretch it to paper thin, or even worse than that, we'd have negative 0.2 down here. Now, it says that it takes a force of 12 newtons to keep it extended 0.04 meters. It doesn't give us a spring constant, but we can find that using just that information. We have f of x equals kx, and we have that the force is 12 newtons to keep it extended 0.04 meters. So that's our distance x. Therefore, we can find k by simply dividing that. And we find k to be 300. So if we use that, we can set up our work formula. I'll use the integral, or the base. If we want to stretch it to 0.3 meters, that means we want to stretch it an additional 0.1 meters past where it is naturally. So that means we're considering a distance from 0 to 0.1 of k, where k is 300, x dx, or 150 x squared from 0 to 0.1. If I plug those values in appropriately, 0 I don't need to worry about, as we've gone over before. If I do 150 times 0.1 squared, 0.1 squared being just 0.01, I get 1.5 joules as my answer. And that's it. That's finding both the spring constant if necessary and also applying a situation involving stretching a spring. Nice and simple. Notice that I use the original integral definition of it because I like myself personally setting it up that way and then solving for the integral. Plus it gives me some extra practice for it. But if you want to use this general equation for it, that should also be just fine. Now, aside from spring questions, which are pretty simple, we can apply the basics of force equals mass times acceleration and work equals force times distance. We can use those to solve a plethora of other problems. We do need to keep in mind a couple other equations that are available to us, such as the equation of mass, which is density times volume. So we can also say that force is also density times volume times acceleration, where density we usually use the lowercase delta. Most of the time, the acceleration we're considering at that point is the acceleration of gravity, which is 9.8 meters per second. If you don't already know that number, keep that number in mind. However, if you are using US standard units, which means foot and pounds and stuff like that, that means the density that you find, the density that would use relative to those units is what is called weight density, which already takes into account the gravitational pull, which means that you do not need to multiply or even consider the acceleration of gravity. So it would just become density times volume. However, if you're using SI units, so meters and things like that, then you would need to consider 9.8 meters per second squared. As an example of this, I have this example 2. Now, this example 2 is very similar to one at the end of section 6.4 in your book. Let me find where it is in your book on the page. 6.4 in your book. It is on page 458. However, this one I'm changing using the US standard units to show how it would be a little bit different. The one in the book that they use the SI units, so they use meters, and therefore they're going to have to use the gravitational constant of 9.8 meters per second squared. For us, this is going to be in US standard, so we do not need to use that, and you'll see. All right, a tank in the shape of a right circular cone is full of water. So a right circular cone looks like this. I'm also going to do it in a little bit of a different way than the book does. If the height of the tank is 10 feet, I think in the book they did 10 meters. If we have 10 feet and the radius of the top is 4 feet, so that means the radius here is 4 feet. Find the work done in pumping the water over the edge and pumping water to 10 feet above the edge of the tank. So we're finding two different work values, one for pumping it up just to the top of it, and one for pumping it 10 feet above the top. So this is important, like if you have water in this tank and you're pumping it up some distance, or if you're just trying to pump it out for any given reason. So you can see a lot of engineering applications to this. Okay, note also that the weight density of water is 62.4 pounds per cubic foot. I believe that the density of water for SI units is 1,000 meters per, or 1,000 grams per cubic meter. So that would be the number that they use in the book. All right, now how we are going to do this. What we're first going to have to try to consider is what kind of disk we want to use, because we are going to use this doing an integral. So if we use a disk like this, then that means the disk is going to what is basically the y-axis, and it's just going to be defined by this function. Know that this is a straight line function, and it's really only going up to this point. We can solve for the equation of this line by considering that point that we know, because this goes up to 10 high and 4 over, so this is 4, 10. So that means we can say that this equation thus is y equals 4/10 y, or 4/10y, or just 2/5 y. Or 2/5 x, sorry. No. It is 4/10y. Yeah. 4y/10. The reason it's 4y/10, if you're thinking about slope in terms of x, you would set this up as y equals rise over run. In this case, it rises 10 and runs 4x. But if you're setting up as x equals, then it would actually be run over rise, and the run is 4/10y. The reason that I want to use the latter is because in this case I have this as my shell and I'm rotating it around, or this is my cross section, I'm rotating this around. So since I'm rotating around the y-axis using disks, then that means I should agree with the axis itself. So I should be in terms of y. So I went 4y/10. So that's going to be the function. Now, to find the volume, which we're going to need the volume because as we had above here, we had that we can find the force by doing the density times the volume. And since we're in US units, we don't need to worry about the acceleration of gravity. We have the density as 62.4, so I'm just going to use that as delta right now. And we have the volume as the whatever this shell is that we create, or this disk. Well, this disk integrated up, we have that that's going to be pi times r squared, where r is 4y/10 squared. And then the thickness of that is going to be defined by delta y. That's going to define the volume of this. So we can then find the work by doing force times the distance. In this case, the integral of the force times the distance. In this case, the distance is how far up I'm traveling. In this case, I'm traveling a distance of 10 minus y. This would be the distance. The reason that we use 10 minus y is the same reason as if we were to try to rotate it around the y equals 10 value. At any given point, wherever I am with this disk, I'm always considering how much further do I need to go. I do need to reach the point up to 10, but how much further I need to go will be subtracted by how far I've traveled. And how far I've traveled is defined by y. So since I have a distance of 10, and I take out y, which is how far I've traveled, I have 10 minus y as how far I need to travel. So that's the distance. If I keep all that in mind, I can find the work by setting up the integral from 0 to 10, because we're going up the y-axis, of 62.4, that's the density, times 4y/10 squared. That delta y is going to be my dy. So I have 10 minus y dy. Okay, we're going to need a little bit more room to work with this. 4/10 is the same as 2/5, so I can simplify that. And 62.4 I can also pull out. Also, I should have pi here because we're rotating this disk around. So this should be pi. Both here and here, yeah. Just didn't have that written down. But I can pull out 62.4 pi outside of that integral because otherwise it's going to get kind of bad. 0 to 10. That's 2/5 y squared, so that's 4y/25, y being squared, times 10 minus y dy. So we get 62.4 pi from 0 to 10. If I multiply that out, I get times 10 would take out a 5 there and put in a 2, so we get 8y squared over 5. Minus another y would give me 4y cubed over 25 dy. Okay, now there's more that you can pull out. You can pull out another over 5 if you want to, but at this point we're fine. 62.4 pi. At this point we should be able to integrate this. 8y squared will make that y into a 3, and the 3 comes to the bottom. So I have 8y cubed over 15. And then 4y cubed, we'll make that 3 into a 4, bring the 4 down, and we'll actually take out the 4 as a coefficient. So we'll have y to the 4th over 25. And that's taken from 0 to 10. Like our previous ones, that 0 doesn't matter. We just need to consider up to 10. So we have 62.4 pi. Put in 10 into y cubed. That gives us 1,000 times 8. So that's 8,000 over 15. And then 10 into y to the 4th gives us 10,000 over 25. Okay, and that, if you approximate that, gives you about 26,138, what we would say is foot-pounds. All right. Now, that would answer the first question. The only difference with the second one of reaching it to 10 feet above where it started, the only thing that would change is this, is the distance. It would not change the bounds of integration, because the bounds of integration is just how much water do I have. I have water from 0 to 10. The only difference is how far that water is traveling. That water is traveling to 20 feet above, so instead of 10 minus y, that would be 20 minus y. So I would solve that for the second part of it. Whoop, let's erase that. For the second part of that question, I would have 62.4 pi from 0 to 10 of 4y squared over 25 times 20 minus y dy, which would be 62.4 pi from 0 to 10 of 4y squared times 20. Again, the 5 should cancel and there's a 4 left over. So that's 16y squared over 5 minus, in that case, 4y squared over 25. So it really just multiplies that part by 2. That's all it does. That I'll leave to you to approximate out and get the integral for that, but you should get something close to 130,690 foot-pounds. Okay. All right, so that's how one of those would go through. And again, this one is similarly done in the book, just with meters instead. And again, because they use SI units and meters, they would need to use the gravitational constant. But we don't have that here because we're actually using weight density. I want to do one more example of this because these can be a little bit tricky. Find the work done in pumping water over the rim of a tank that is 50 feet long and has a semicircular end of radius 10 feet if the tank is filled to a depth of 7 feet. Okay, well first we have to draw that. So semicircular end, so it looks like this, looks like a trough, and it's 50 feet long. So something like this. See how I can draw this. And then like so. That's not too bad. I think it's one of my better drawings. It says that we have a radius of 10 feet, so that means from here to here, this is 10 feet distance, and it's 50 feet long, so 50 feet this way. Now I'll actually put that 50 feet over on this side here, because the way that I'm going to draw this, I want to make this as simple as possible. So let's make the middle of that trough where I would say the distance, I'll make that the x and y axis. So right there, that's where I'll situate this shape. Now, it says also that the tank is only filled to a depth of 7 feet, so that means it only has 7 feet of water, or down to -3 is where water is, so it's not completely filled. Maybe I'll actually do the blue for that. There we go. Water's blue. Okay, so that's how much water I have. It's not completely filled. Okay, well, we have the drawing in place, so now we should be able to solve this. Again, we want to consider force as the density times the volume. We know the density of water from the previous question is 62.4 rather. And then for the volume, we consider what my cross-section is. In this case, the cross-section that I'm working with is like this, or actually even more accurately, I'm working with a cross-section like this. So what that means, if I were to consider that going all the way down, this being my cross-section, this is just a rectangle. And rectangles are really easy to find the volume for. The volume of this is going to be represented by the length of it. The length is easy. The length is 50 feet. So I'll just say 50. The width of it is a little bit complicated. The width right here is going to be defined by whatever this function is. Since I know that this is something with a radius of 10, then that means I know I should be able to define this as 10 squared equals x squared plus y squared. Since I'm defining a slice like this and it's going up the y-axis, I'm also going to put it in terms of y. So we'll say that this is y equals the square root of, it would be 100 is 10 squared minus x squared. So we have that, but we're also going to need to double it so I can consider both of them. So 2 times the square root of 100 minus x squared. That'd be the length. This would be the width of it. Again, we're doing 2 so I can get double this. If I try to do the full cross-section over here, that means I'd have a cross-section that goes from the function to itself, which I don't really want. And then the width, we have the length, the width, and then the height, I guess. The height of this is going to be delta y, where delta y is approaching 0. If delta y is approaching 0, that's where we get our integration. That's where we get our limits. Again, we don't need to do anything with gravity because 62.4 is already taking into account because that's weight density. Lastly, we have the distance that we are traveling. The distance that we are traveling is actually really, really nice because of how we set up this problem. The distance that we are traveling is going to be defined by how far away we are at any given point. And since we set this up to go below the x-axis, then that means that the distance that we actually are is a distance of negative y. So when we set up the work as the force times the distance, that means we have 62.4 times 50 times 2, which is 100. So that's 6240. Yep. Times the square root of 100 minus x squared delta y. That would be the force. And then the distance would be negative y. That's how far we're traveling. All right, so let's work with that. Now we may need to adjust some of these numbers depending on what happens with our integral, but we'll see. So my work integral is going to be, in this case, from negative 10, because that's how deep the water goes, up to negative 3, because I don't have all the water. It only goes up to that. There's only 7 feet of it. And we can actually put the 6240 out front. So 6240 of negative 10, negative 3, of the square root of 100 minus x squared. Delta y is going to be my dy, and so I have also negative y times dy. Oh, sorry, these should be all in terms of y, not x's. Y, and that one in terms of y as well. I even said earlier I was going to put these in terms of y. So x. There we go. Okay. Now, if I wanted to solve this, this is a little bit complicated to solve. It's not just a standard polynomial. What I do notice, however, is here I could try to make this easier by doing a u substitution, saying u is 100 minus y squared. If that's u, then that means du is negative 2y dy. Well, I can figure that out as du over 2 is negative y dy, which is what I have right there. So I can set this up instead as all of this divided by 2, which is really going to influence the constant there. So I'm going to introduce a division of 2 here to make 3120 of the square root of u du. Now, when I went through the u substitution before in 6.1, I recommended that you do not resubstitute back in, particularly if you have bounds. If you have bounds, you should just be able to use those bounds and find the new values. So u for negative 3 for my upper bound. If I plug in negative 3 into here, I have 100 minus 9, which is 91. And then if I have u times negative 10, or u of negative 10, I plug in negative 10 into here. That's 100 minus 100 is 0. So this is now 0 up to 91. That's a lot better, so that when I solve this, I get 3120 times u is u to the 1/2. So that's 2/3 u to the 3/2 integrated from 0 to 91. 0 is nice because that makes it a lot easier. I don't even need to consider it. I just need to consider the 91. 3120 divided by 3 is 1040 times 2 is 2080 times 91 to the 3/2, which I don't know the square root of 91 off the top of my head, so this would be fine as a solution, or we can approximate this. So we'll say 2080 times 91 to the 3/2. We get approximately 1,805,616. And again, that would be foot-pounds. All right, so that would be another situation of working through a problem involving work. With that said, that's everything with section 6.4. If you have any questions, feel free to put those in the comments below or ask your instructor directly. I hope you have a nice day.